You are rolling.
All right, so here's the last talk of the day. You guys ready for some power analysis for software hackers?
Yeah!
It's Breaking Encryption with an Oscilloscope by Tim Dewar and Alex Balducci. Please give them a warm toorcon welcome.
Thanks for sticking around, everybody.
Yes, thank you for coming back.
This is, like I said, Breaking Encryption with an Oscilloscope.
Speak up.
Can everybody hear me?
You're fine
Okay.
before.
So me and Tim both work at Montesano. If you want to contact us, our emails are on the page. So let's just jump right into this. So what is power analysis? Anybody? No? Okay.
Anybody?
Yeah, exactly.
All right, work job's done. See you guys later.
So this is a form of side channel attack. And I'm sure you're all familiar with timing attacks, which is one version of this. We also have cool things like fault analysis. So when crypto systems are operating, we can supply extra heat or voltage to influence the operation, and we can determine secret keys from that. There's also data remnants attacks where, you think you delete your data, I get access to your hard drive, I can capture your secret keys from that. Acoustic cryptanalysis, which is most like power analysis. It's really cool research done there. I would suggest everybody check out that link. But that is figuring out like RSA keys by analyzing the noise that the vibrations of your hardware are emitting. But the main characteristic of all these attacks are we're breaking crypto systems because of their implementation, because of the engineers who are building these, and not like actual crypto flaws. These are things that cryptographers generally do not think about.
Yeah, we're exploiting the physical realities of the device instead of the device itself.
So that brings us to power analysis, where it's simple. Power consumption reveals secrets. So when a device is operating, it's operating on, a lot of times in the crypto sense, secret keys, secret data, and depending what those values are, it's going to affect the power consumption. Likewise, depending on which operations are actually being performed, moves, XORs, that's also going to have its own unique characteristic that we should be able to see if we are analyzing and reading the power consumption.
So most of the time, any of the stuff that we're going to get access to have to do this kind of thing is going to be consumer-oriented devices, stuff like power meters. If you've seen some of that stuff go out, they're huge mesh networks now where they don't send a guy out to your house anymore. They just like send out a radio signal and get a bunch of pings back. Smart cards actually did some of the first research on this. Was on smart cards, RFID systems, NFC systems, just about any embedded piece of hardware, gaming consoles, stuff like that, where you're not looking at a high security, high speed device because, well, let's face it, that's not they're not going to come to me for that. They're going to go to somebody that's been doing this since the beginning that has their patents on it, basically. Which gets us into a little bit of history. If you can see, this stuff starts in 1998. It's actually a very old attack as far as these things go. But it's basically a war between the cryptographers and the engineers. There's a lot of work between what goes on in actually implementing the stuff in silicon and the algorithm itself. And basically, Paul Kocher, when he started doing this stuff, thought to himself, what information is available that the cryptographers haven't thought about? What happens when you look at everything in this system and not just the math? That's me for business. What do you know? So what is this stuff we're looking at? Well, obviously, we're going to have to define things. I think it's a requirement for this kind of thing to have a slide like this with a really pointless definition on it. So hardware is a physical device. It's all the diodes and transistors and other bits that make up an electronic system. Software is the stuff that runs on it, obviously. All know what software is because that's our job, right? What are we actually talking about here? If you look at the schematic, it's basically the schematic of every device that's out there. This one particularly is a Arduino clone, but it could be any of the systems that we're going to wind up looking at. It's a microcontroller, a power supply, and its peripherals. Stuff like serial ports going to some environmental monitor chip, things like that. And right now, because of where everything's come down, we're really looking at firmware, and even this definition, which I pulled out of OS X, is out of date. It's no longer read-only memory, but that doesn't really matter for us right here. We're looking at stuff that was written as code and then pushed onto a device that will run it later, a more general purpose device, not something that's designed specifically for doing these cryptographic operations, which is kind of what helps us out here a lot. And what we're exploiting here is the different paths in the silicon. When any operation occurs on a microprocessor or a microcontroller, it takes a slightly different path through it, not only based on the operation itself, but also the inputs to that operation. It's going to take a little bit different path, and if it's taking a different path, it's going through maybe more transistors, fewer transistors than other ones, so it's going to have its own fingerprint. Even the traces that it goes through is going to have slightly different variances in the amount of power it consumes based on that operation and that input. Unfortunately, we're never going to have a scope that's quite that good because, well, I'd rather have a house than that kind of a thing. But, and like I said, we're not going to get tasked with that kind of hardware. We're looking at stuff that you can get cheap. The scope that we're actually going to use here is $700, and that's about $400 more than it needed to be because I wanted to have something in the office that was actually useful and had a logic analyzer on it.
So we're going to get into actually performing the attacks a little later in the talk. But first, we have to talk about modeling power consumption. So what I'm talking about here is, can we get a general sense of how much power it takes to operate on a secret key or with some operation that's being performed in the device? So we have a couple methods of doing this, which the first one would be the Hamming weight. So just imagine a bus or a register holds this value. We just count the number of bits. We're just assuming that 1 bits take more power to hold in the bus or the register over 0 bits. And granted, this is a very crude model. We'll see later that it is effective at actually modeling power. Our other more advanced one is the Hamming distance, where we're counting bit changes over a time period. So the first was just thinking, Hamming weight was thinking about a particular value at a particular point in time. But using the Hamming distance, we can kind of get a general sense of how power changes over the course of 2 timestamps. So this is also very simple. There's time 1 that holds this value up here. At time 2, we measure it again. We can count the bit changes, which is the same thing as doing an XOR. And then we just take the Hamming weight of that. So we will see later that, granted, these power models are simple, but they give us a lot of information that we can tie to the traces to actually then attack these devices.
So from here, we're actually going to get into a lot of what we're really doing here. We're going to start with a little bit of overview about the equipment and stuff that we're going to use, and then go into setup, where we need to connect things, what we need to know a little bit about that kind of thing. Go into actual data acquisition, some of the tools that I wrote to do this kind of stuff, to help out some of the other ones that are available, and how to extend what exists a little bit yourself, depending on the actual needs of the device you're attacking. And then
Alex is going to cover all the analysis bits, where you're taking the data you've gotten and turning it into a key. So we're going to start off with the tools. Like I mentioned earlier, we need an oscilloscope. The kind of stuff we're targeting is low-end, consumer-grade stuff where, it's the processor that's in somebody's watch. It's the processor that's in that or the microcontroller that's in that power meter, things like that, that are running at like 2,000 megahertz or 200 megahertz, not 2,000, not even 200, 20 megahertz, 10 megahertz, that kind of thing. The cheap stuff that costs like a dime, maybe 50 cents on the high end per chip to do. So we've got like the cheapest oscilloscope you can get with a logic analyzer in it, and that's really all you need. So we're going to use this to dump a vector of the voltage used and the voltage drop across a resistor. So that's going to give us the current drawn by the device at each sample in time across, I think the range is like half a second, but the operation doesn't even take that long. So, but it's going to give us samples of the power consumption through in multiple samples per clock cycle across the entire thing. So we can do this correlation in a bit. To do that, we need to know a little bit about our options for oscilloscope equipment. Like I said, this kind of stuff we're going after. We're not going after the chip in this MacBook. We're going after the chip on this launchpad type of level of thing. So we just need the cheapest scope you can get, and that's basically enough for anything up to 20 megahertz. But the probes are where things come in handy and become important. You've got basically three choices. There's the analog probes. They're passive probes. They're actually what we're using for this demo right here. There are active differential probes, and then you can also just look at the electromagnetic emissions. I can't talk today, apparently. You can look at the EMI radiation from the device as well to get because it correlates straight with the power consumption itself. So you can just use that as well. Passive probes, the great thing is they come with the oscilloscope. There's no oscilloscope I know of, and I'm guessing the only ones that don't come with a set of passive probes probably cost $20,000, and the probes themselves are probably a good couple of grand at least. So anything you get like this is going to have a pair. The downside is that you will need two probes. You need to get the voltage drop across a resistor to figure out the current used by the device. So you have to get the voltage on the high side and the low side of something, which in most cases is going to half the bandwidth of your scope. You're going to get half as many samples across that time because you have to get two at each spot. It is also will introduce the most noise. These cables are really long. They're adding a lot of strain to the circuit itself, things like that. You can make them yourself, but why would you? It's really cheap, it's really easy, but they come with a scope. If you have to replace them, they're like $50. But as much as unless any of you guys decide to get a hobby in electrical engineering after you try this kind of stuff, which honestly I started doing myself and it's kind of cool, so go for it. But unless that's the case and you start doing this a lot, you'll never need to replace the pair that comes with your scope. So making them yourself is not really something worth considering. We get into active differential probes next. These are probably the best way to sort of the best middle ground for an option there. They are ridiculously expensive. Like the cheapest one I could find is twice the cost of the scope, which I didn't want to try to expense at all. So what you see there is a picture of somebody else's circuit for one that they've published. I've got a link in that was actually supposed to go on the slide, but it hasn't yet. It's in the speaker notes that I can get to anybody that needs them. We'll actually have the slides up on our site eventually. But so that circuit does 250 megahertz bandwidth, which is more than enough for any device you're going to look at. That's more than 10 times what you need. It's very low noise, and as long as you are not doing the design yourself, it's it's not easy, but it's not ridiculously hard, especially if you're comfortable soldering, surface mount stuff. If you're not comfortable soldering surface mount stuff, you can put a little bit of money behind it and have somebody manufacture the thing yourself. It'll cost you like $100 from start to end. Otherwise, it's maybe $20, $50 to have somebody make the PCB and then get all the components to populate it yourself. So it's really not that bad for cost if you're doing it yourself. If you decide you need to design one yourself, and you don't have any experience yourself doing analog high-speed circuits, I'd suggest doing that as a hobby maybe, but don't expect to do it without going back to school for a little while to get an electrical engineering degree. But for the most part, you don't need to. Like I said, the circuit's going to be more than enough than anything you need. There's also EMI probes, which kind of surprised me at how expensive they are. They're about the same for a really good set. You can get a cheap knockoff set that I honestly would rather just make my own than buy for $100. But if you're getting one that's designed for this kind of work, you're looking at, I think the cheapest one I saw was 1,500 euros, which again is way more than twice the cost of the scope. So you're really better off making them yourself. If you're not, when tuned properly, these are going to be the least noise that you have to deal with, because you can get a very small loop sitting right over the spot on the chip that is actually performing the calculations. It takes a little bit of work to find that spot, but once you do, that's going to be the best for noise you will ever get, because you're right on top of the source that is doing the work, that is consuming the power. Any of these other options aren't going to be that close, so they're going to have other components adding to what's going on there. If you're willing to deal with just a little bit more noise, they're really easy and cheap to make yourself. It's literally a question of going out and buying a short chunk of coaxial cable and stripping off some of the wiring and soldering it back together into a loop. That's it there. It's really dead simple. It's really cheap. And then you need a resistor. And yes, I had to put up a slide for a resistor. It seems like a waste, but sometimes you got to do what you got to do. When you're choosing one, you want something fairly low, because you don't want to put too many restriction. You don't want to put too high a restriction on the amount of current the device can get, because you're adding extra consumption to it to get a difference based on how much current the device under test is drawing. And you also want a fairly round number so that the math is easier. You're going to eventually divide this out. If you don't know Ohm's law, V equals IR. So you need to get to the current, you need to divide the voltage by the value of the resistor. So you might as well make it a nice round number like 10, which is what I'm using here. And that's really all you need. Is you need an oscilloscope that you can get digital data, that you can get the data out of in some digital formula that you can do math with, and a resistor and the device you need to work with. Then we're going to get into the setup. The first thing that you have to worry about here is what you're actually looking at. And sometimes it's easy enough to know, this is the device I have. I've got a launch pad. They tell me exactly what chip is on it and stuff like that. Sometimes in a actual job where you'd be getting a device from somebody else and looking at it, maybe they didn't give you all of the specs. Maybe they just handed you the device and said 1, 2, 3, go. And in that case, you're going to have to take a close look at the chip. And if you can see on here, on the upper left corner, you can see Texas Instruments logo. That's a pretty dead giveaway on a lot of this stuff. Is the manufacturer of the device is going to tell you a lot about what it probably is. In this case, if it's Texas Instruments, it's more than likely one of two things. Either it's an MSP 430, or it's a ARM chip. That's basically your two choices for microcontrollers at Texas Instruments. On top of that, because this also isn't a surface mount chip, and it's not a really small surface mount chip, you've got a actual model number on it. That's the bottom line there. The top line is a bunch of manufacturing information that really doesn't matter for most of this stuff. There might be a chip or two here and there, a revision, where it might tell you a little bit more about how to attack the device, but that's very unlikely. The interesting information is what's below there, the M430G2553. So you're gonna look that up, and usually like the first link you get on Google of M430G2553 data sheet is going to be a document like this. And if we go to the right application, you can see this is actually the short version of this data, and that is not what's on the screen. So this is actually the short version of the data sheet at 120 pages. And it's got all kinds of nifty stuff on it. What you're looking for is, if you saw on that slide, usually a couple of pages down, this thing. This is the pin layout of the device. It tells you what all of the pins on it do. You are interested in exactly 2 pins, ground and VCC. You need to get in front of VCC. VCC is where you need to get a resistor in front of some known value. Maybe you're lucky enough that it's already in the circuit. You might have to do some creative soldering, go in there, cut a trace, resolder stuff. Hopefully you didn't have too much coffee that day. If you did, go get a drink, take some time. Not always a fun thing to sit there with an X-Acto knife, scrape off some traces, and then try to solder in something on a very thin trace. But sometimes, and especially when you're just playing with it yourself, you're lucky enough to have a launch pad like this where they've got a nice pin for that. And I'll show you in a little bit, on this thing, it's just a question of going in there and sticking a resistor into 2 other things. From there, you're going to want to make sure your scope is calibrated properly. You're going to make sure that the trace while the operation is going on, because the device is going to use different amounts of power, even not only like on every operation, but if it's sitting idle, it'll be at one level of consumption, and you'll see in a bit when it's actually doing the cryptographic operations, it's going to use a little bit more power. So you'll see a different current draw on that kind of stuff when that happens, and you're going to want to zoom in as much as possible. Obviously, you want the scope to be set to capture as much data as possible, so you're better off throwing out data than you are trying to make up for data that you don't have. And then you're also going to need a way to interface with a scope. Obviously, this is a bit of a shameless plug. I wrote, when I first started doing this, I looked at the Ruby bindings because I like Ruby. We're a Ruby shop as much as people like Alex would like to deny that and use Python. So I started using the Ruby bindings that already existed, and I found out that they barely implement enough of the VC library to do anything. So I rewrote a bunch of that stuff, and that's AirB. And then on top of that, on top of those bindings, I wrote a library specifically for this scope and the operations on it, which if you guys have any suggestions for names that are better than DS1102D, which is the model number of the scope, I'm all ears. Just let me know afterwards. And then if you're stuck in Python, obviously there are no bindings specifically set up for this scope or any scope actually. You'll have to look at the manual and go through that stuff. But there's the PyVisa library. Any of you guys that are actually looking at GitHub right now, trying to find those 2 libraries under my repository, my 2 repositories are going to be missing something because they haven't had a chance to put it up yet. And then, so we're going to look at some of this stuff now, and hopefully I put that on the right thing. So we've got the scope here. It is unfortunately reversed because, well, Radio Shack only carries a certain webcam that only works on Windows fully. So if you're going to fire up the mic, it's going to crash. So Photo Booth is surprisingly the only really fast way to get a image without firing up the mic. So you'll have to deal with it being reversed, but for the most part, that's not going to matter. I've got here the pointer in the wrong spot. Put up here the libraries I've got. So unfortunately, currently my library requires an extension or a version of FFI that I haven't merged yet, but and I can't type. So what we've got here is a global that I still can't type. Global that's got a bunch of stuff set up. I'll hop over to the code. You can see in the instance variables there, I've got a object in there to talk to the 430 I'm using here that has a implementation of des on it. I have that is the board instance variable. The session instance variable is the oscilloscope. That's the more interesting one for us right now. So equals OSC dot session, and so this has this is using the DS1102D library, so I can do stuff like sesh dot waveform dot channel 1, and that's of course the wrong one. So I can use all of the functions on the device to pull up the various information I need off of it, which I've got here. So if we look up here, I need to pull, because I own the device, I'm cheating and pulling the plain text off of the target board itself so that I can compare later and make sure I'm doing what I think I'm doing. The next line tells it to perform the encryption routine. It is helpful to know when exactly the encryption routine is happening. If you don't, and most of the time you're actually performing an attack like this, you're not necessarily going to. You might be lucky and like me have a LED or something like that flashes. Obviously, I made it do that flashing right before the encryption is going to happen. Otherwise, you're not. And Alex is going to cover in a little bit what to do when your traces don't start when the encryption starts. The next thing I'm pulling here is the wrong key that I keep pressing, and that's actually pulling the digital the logic analyzer channels, so I can trim down the traces themselves to just the encryption operation. And then the next two lines are the scale and offset of the time on the system, so that I know from the oscilloscope how much time has transpired between each tick and when exactly in the trace it starts. The next two are querying the first analog channel, what the scale is and what the voltage offset is, and we'll see that on the scope in just a little bit. You're going to want to, like I mentioned earlier, you're going to want to narrow it down to holding so that on the screen is exactly as much of just the range during the encryption operation as possible. so that you can get as much detail as possible without having to do it, so you get more information out of it. Next one is just the same thing for the second analog channel, and we're going to pull the actual traces themselves. This is all of the data that is that squiggle on the scope when you're getting it. And if you were to see the actual commands going to the oscilloscope itself, it looks a lot like these themselves. It's like colon waveform, colon data, question mark, channel 1 or something like that. I don't remember because I looked at that quite a while ago to write this stuff and forgot. I'm also going to take a look at what it's triggering on just to make sure, so we can keep track of that, get the same digital information. Actually, that line's not needed. And then I'm actually not pulling the data here. Anyway, we're going to pull the digital channel waveform as well. Actually, that was way up top. Wow, that's out of order. Pulling out the information from the digital channel so we can turn these down, and then also what the sampling rate is, so we know so we can figure out where in each trace everything is as we need to. So I'm going to switch over to the oscilloscope now as soon as I actually start. Let me see. Let's put a good chunk of zeros on there. So this thing is set up to do this on a get. osc.get. I'm just telling it to 1,000 times, and I missed an S, 10,000 times even. Just run through this and get tell the target board to pull up to perform the encryption function so I can calibrate the scope and get it all set up. osc dot board dot encrypt. Wait. Okay, that's happening, and that's not working. Awesome. So, fortunately, if I can find my stuff. Haha, video. I swear I actually performed the proper sacrifices this morning to, the live demo gods. There was a half a chicken and, 7/6 of a goat, and apparently that wasn't enough, or maybe they wanted lamb instead, I don't know. So we're going to start out with, I've got it set up to trigger on those digital channels, and I didn't start in the right spot, apparently. So I'm going to sit there, and you see that blue line on the top? That's the analog channel that's attached to the low end of the resistor, and I'm zeroing in on where the entire trace is. You can see there, right in the middle is where the encryption starts to happen, and the consumption goes up quite a bit. You can see the trace going down a bunch. Now I'm just narrowing in step by step to get down as granular as possible. I'm actually going to go as low as the scope goes at a scale of 20 millivolts. You can see here, I'm going to scroll over, and you can see this is actually a very noisy signal right now. You can't see a whole lot of what's going on, but you can also kind of see that as I go through this, there are areas where there's definitely something going on. In this particular case, I haven't told it to continually change the encryption, so there are spots where the same thing is happening. And you can tell even outside of the noise, and watch that some of the stuff is going on. I'm going to go in a little bit further, and then so basically once you've got that set up, you can use the libraries that I've talked about to pull traces. You're going to wrap wrap a loop around just polling the oscilloscope for information and to get as much data as possible. Based on your power model and stuff like that, you'll know about how many traces you need to pull up and stuff. Without that, you wrap a loop around that and just stick it in a database for use later.
Okay, so now let's actually attack these things. So you saw that those traces that Timur was taking, like you mentioned, were pretty noisy. But what happens if we get something that is pretty clear? And this is our first form of analysis, which is simple power analysis. Here, it only takes a few traces. We're talking like 1 to 5. And the only tool that we usually use here is just our eyeballs. And we're trying to look for some type of data dependence, somewhere where secret material, whether it be like nonces or subkeys or intermediate rounds of ciphertext are used, and we can find where in the power trace the power differs because of what is being operated on. So we're looking for obvious power differences, timings, branches, what have you. So this is what a very nice trace will look like. And we really can't do much with one trace, but we can get some characteristics of what is going on, what algorithm is being used, how long it takes, etc. So we see around the 1 millisecond mark here, 16 peaks come afterwards. So this corresponds possibly to 16 rounds of DES. The stuff beforehand is maybe plain text being copied into whatever space operations could be on, and then the very end where the 16 peaks stop, maybe where ciphertext is being output. Other than that, we can't really do much with one trace. If we have multiple traces, we can, like I said before, compare them with our eyeballs. So what we want to do is line them up so we know that the encryption operation starts at time 1 for both of these. And let's look down each until we see if there are any differences. So up until about the 6.5 mark, they're relatively, they're pretty much the same. But we see this in the top half at 6.5, there's a big power consumption there, and on the bottom trace, there's a low one. So we can maybe think that this is possibly like some branching, depending on maybe like a nonce is used. And depending on what type of system you're looking at, that might be exploitable, and you might be able to figure out some secret key or the plain text or what have you. So a better example is attacking RSA. Now RSA works if we have a ciphertext. To decrypt that message, we raise it to our secret key, which is D, mod n, the public modulus. Now we want to have a efficient modular exponentiation, and one admittedly bad way is square and multiply.
So incidentally, if you take a math class in cryptography, like an introduction, this is actually the algorithm you're going to wind up using. I don't get it, but let's use the weakest one, you know?
So for this one to work, we're going to run through each bit of the exponent, which in this case is our secret key. And we're always going to do this squaring operation. Now, if the bit that we're currently at in the exponent is a 1, we also do a multiply operation. So is this bad? Well, let's take a look at this. You see these green peaks. Well, the smaller peaks here, we can determine are the square operations, taking less power than the bigger peaks, which are the multiply operations. So just from this power trace, we can run down the line of these, and we can literally just read out your secret key. Going from small peak, we know it's a 0. A small peak followed by a big peak, we know it's a square and multiply. So that's a 1 bit in your private key. And literally just reading it off of the trace itself. Now, most of the time, we're not that lucky. This is where differential power analysis comes in. And this is where those power models that I talked about before. So again, what are we after here? We're after keys, we're after plain text, we're after subkeys. We're not lucky enough to have the simple things that we can easily observe, but there's still a small but present correlation between those secret values and the power consumption. Granted, we can't see it, it exists. So if we're able to capture many traces and use some statistics, we can hopefully determine keys, subkeys, and what have you. So to perform this analysis, we have a couple steps. First, we have to actually acquire traces and do some post-processing of those. Then we're actually analyzing the target. We're trying to figure out what algorithm is being used, what part of that we're attacking. So if it's DES or AES, can we attack one particular subkey of that? How are we going to do that? What power model are we going to use? Is it going to be a Hamming weight? Is it going to be a Hamming distance? And then finally, we're going to actually perform that analysis. So the first step is collecting traces. If you don't have an oscilloscope, you can go to dpacontest.org. It's kind of bizarre that such a thing exists, but it's really cool. They have it's like 4 million sample traces for DES operations, many more for AES, many more for AES with masking. So it's a good thing to just pull these off. They're like 6 gigabytes, but then you can just muck around with it and actually implement some of these attacks without having to go out and buy a scope. So a lot of times you get those traces and there's just way too much information. It's way too redundant. What we're looking at here is the hardware is only be able to perform so much in a clock cycle, and the oscilloscope is going to measure a lot more voltage points in that clock cycle. So we wanted to remove that redundancy, because that's going to help our analysis later. Otherwise, it's going to be pretty computational.
And have a lot more noise.
Yeah. So one simple way to do it, or these are a couple simple ways to do it. Within that clock cycle, we could just take the max value of the power consumption in there. We could sum the values, sum absolute values, or we could sum the squares. I found that all these techniques work relatively well in what we've been attacking. The second thing you have to do is actually align the traces. To do the analysis, of course, you want each trace to start at the same time at the start of the crypto operation and end at the same time at the end of the crypto operation. Like Timur was saying before, you're going to get a lot of crud before the trace starts and after the trace ends, where it's like winding up, entering the plain text and then like outputting the ciphertext. So what we do is we take one trace and we treat it as a template. We mark that at time instance 500 in the trace is where the crypto operation starts, and at time instance 1000 it ends. And then for each other trace, we take that trace and we subtract it from our template trace. Then we sum the square of the resultant vector. If that's at a minimum, we know that they're lined up. If that's not a minimum, we will slide the trace that's not the template over, we'll subtract it again, take the squares, and then sum. And when that sum is at a minimum, we know that our trace is aligned. So then we'll do that for every single trace that we acquire. Next, we have to actually analyze the target, find out where and what we're actually attacking here. So first, what data do we have? In our scenario, we have ciphertext and we have the power trace information. And it should be noted that these are many different distinct ciphertexts. Then we have to think about what algorithm that the cryptographic device is performing. So in this case, it's DES. I'm going to explain in a second how DES works, but we're going to actually be attacking a subkey. And why do we want to do that? Well, we need to form a power model where we relate the crypto secrets, in this case the subkey, and the ciphertext, to our trace information. And that's the point of the power model. It's the connection between the analysis and the power information. So here's an outline of how DES works. You have a 64-bit plaintext entering it, and you have a 64-bit key. This key is split up into 16 subkeys, one for each round of operation. So plaintext comes in, stuff happens, and you get what I call an intermediate round of ciphertext. It works its way down until the 15th round of ciphertext, and then its finally output is just the 16th round ciphertext. So if you remember the Hamming distance model, we have, we're measuring the bit differences between, say, a register or a bus or something at one time, and then we're measuring it at another time. And we're using those in the model. So one good, since we have the ciphertext here, we can use the Hamming distance model between the ciphertext and the intermediate round 15 ciphertext. If you look back, there's this F function here. This is where those subkeys actually come into play, and I'm going to describe that in this next slide. So only 32 bits of the intermediate ciphertext comes into this F function. It gets expanded, then XORed with the subkey, sent through these X boxes, and then its output. So the output that we're looking at is the ciphertext that we know. If we knew the subkey, we could work back to that intermediate round ciphertext by going the reverse direction. But we don't. But we can guess what the subkey is. If you look at the S boxes here, they're all independent. Only 6 bits from the XORing between the block of intermediate ciphertext and the subkey go into each one of them. They don't depend on each other. So we can actually attack those one at a time. So we look at the first S box, which is 6 bits in from the subkey and the intermediate ciphertext. If we can guess what those 6 bits are, we can work our way back to that intermediate ciphertext and form our power model. Now, so when we're performing this analysis, we're only going to target one of those S boxes. And since there's only 64 possible keys, we can easily work backwards from our ciphertext to that intermediate ciphertext, 1 for each possible key, so 64, and we can figure out the Hamming distance between those 2 pieces of ciphertext. That's going to allow us to then compare and use that to correlate to our trace information. So to repeat myself a little bit, we're after this purple box, these 4 bits of the ciphertext in the intermediate round. We know these 4 bits because that's the output ciphertext that we're given. And we're guessing 6 bits of the subkey, 64 possible values to get back to the purple box, those 4 bits of the intermediate one. So before we continue to attack, we'd like to verify our model. And here I'm imagining that we have a device that we control fully, that we can enter whatever keys we want. We can enter any plain text we want, and we know it. And of course, we know the ciphertext. So we can, again, use the Hamming distance model to verify this. So we can collect traces, and since we know the plain text, and since we know the keys, we can actually calculate the correct 15th value intermediate ciphertext. Using that, we can calculate the Hamming distance between that and the ciphertext that's output from the operation. And then we will compare that, each Hamming distance, to the average peak power that corresponds in the power trace that we got from the oscilloscope. So this shows that, where the bottom axis is the Hamming distance of an operation, and the y-axis is the power consumption. So what we can see here is like Hamming distance 6. So only 6 bits are set. It does not take a lot of power. But up at Hamming distance 27 bits are set. It does take a lot of power. This proves that the Hamming distance model in this case will actually work, and there is this dependence between bit set and the power information. What you would want if you were designing a secure device is, of course, a straight horizontal line. So now actually performing the analysis, we're going to create for each possible key, we're creating two different vectors or buckets. One is going to correspond to if the Hamming distance is greater than 2, and 1 if it's less than 2. Then we're going to run through each trace in each ciphertext. We're going to calculate the 15th round ciphertext by working backwards with the key guess. We're going to calculate the Hamming distance between those two. Then we're going to add that whole trace information to that appropriate bucket. Maybe a little more clear in code. We have two vectors indexed by the key guess, so 0 through 64. Then they also will contain the whole trace power information in it. So then we're going to loop through each trace, each ciphertext, and then we're going to loop through each possible key guess. Work backwards from the ciphertext we have using our key guess. We're going to calculate the Hamming distance. Then we're going to add that whole power information to that particular trace. So for instance, for key guess hex 24, we have a trace. We're going to work backwards. In this case, the Hamming distance is less than 2. We add it to the less than 2 bucket. In this case, we add it to the greater than 2 bucket. And then remember, each key guess is going to have 2 buckets corresponding to it. To finish it off, we just subtract the 2 buckets for each key guess. Then whichever resultant vector has the maximum, that will signify the key. So let's take a look at what that looks like. The trace at top here is an actual trace from the device. The bottom 3 are the resultant vectors for particular key guesses after subtracting them. So we can see the bottom 2 look like basically noise. There's no correlation, there's nothing there. But the second one, we see that big peak, and that signifies to us that is the correct key. So why does that actually work? When we guess an incorrect key, we get incorrect partitioning between those 2 buckets. So half the vectors will go to the wrong traces. We'll calculate that Hamming distance incorrectly. The other half will guess correctly. But subtracting that should average it out. And that's why you saw that it basically looks like noise on these bottom 2 traces. But if we have the correct key, we do get correct partitioning. We are calculating the Hamming distance correctly. So all those buckets, those 2 vectors for that particular key, will contain the correct traces. And after subtracting them out, we will get a little peak. It's not going to be all noise. Here's a graph showing the max of each vector after subtracting them together for each key guess. And we can see here at like 61, it's an obvious winner that it has the max power there. So then we know that 61 is the correct key guess. One final form of attack is template attacks. This is kind of the best you can do in power analysis, and it's an offline attack. So here we're assuming that we have in our lab the exact same device that we're going to be attacking out in the wild. This allows us to form these templates, which when we actually attack the device in the wild, we will need few traces from it. But it's computationally expensive to form these templates in the lab. So what do? We do some math. We can treat each trace as a multivariate Gaussian distribution. What does that mean? I don't know. But it gives us
Anybody here actually know what that says? I mean, I do, because I took a whole lot of math. Yeah, one person, okay.
But it gives us a probability function that we can use, and we can apply that to each trace and get a probability that that trace corresponds to a particular key. So what do? We take a lot of traces in the lab, and we group traces by Hamming distance. We calculate the mean of each group for each Hamming distance. We calculate the covariance matrix of each group, and then that pair is our template. Then when we're attacking in the wild, we just gather just a couple of traces. We use that probability function, and for each trace we get, we update it with that new probability. And then finally, after just a couple of traces, we'll be able to determine the key. So some stats of how many traces this actually takes. Attacking DES with the Hamming distance model, 320 traces. CPA, which I didn't talk about, but it's really close to the Hamming distance model.
That's also more math.
260 traces. AES with CPA is 4,700, and you can see how well template attacks perform. It's a whole magnitude better with only 430 traces when attacking AES.
So how do we prevent against this stuff? You know, when we get to the end of the test, you know, we wind up with this wonderful report that says your stuff is broken, at least if we're doing our job right. But we also then have to follow that up with, you know, what do you do about it? And unfortunately, in the case of power consumption or power analysis attacks, there's really two options. There's masking and there's blinding. And unfortunately, as you can tell from that first bullet, the correct answer is to talk to Cryptography Research Incorporated because they own the patents on it. They're actually really good at what they do. They're the company that actually started all of this stuff, so they are the front of everything. So if somebody is particularly worried about it, you're going to want to tell them to go to CRI and get a proper solution for that kind of thing. Otherwise, you're going to look to obfuscating things or adding a whole bunch more noise. In the case of preventing simple power analysis, really the only thing you need to do is change the algorithm that you use to make sure that the same operations get performed at the same time. So instead of using the naive version that was up there that you wind up getting if, like I said, you take a math course that is Introduction to Cryptography, which I took and I know from experience, that's the algorithm you get taught. If you don't use that, you set up an algorithm so that every time every step through it, every bit you're looking at, you do both a square and a multiply. That noise goes away, and you're pretty much stopped any simple power analysis attacks. Past that, it gets a lot nastier. Just adding noise isn't quite enough. You really need to get into blinding and masking themselves, and while adding noise will help, it just means they have to buy a slightly better oscilloscope. So instead of spending, $400, they spend $1,000, maybe $10,000 if they really want to throw a lot of money at it, and they've gotten around your little bit of extra noise. Your options then become blinding and masking. Blinding is setting up some math ahead of time. What you're going to do is you're going to change the input to the function. I'm getting these reversed again, aren't I?
That's sort of right.
Sort of right?
I get them reversed too.
Yeah. So you're going to change the, one of these is right for one of them, so don't quote me too much on it. He's the crypto guy, I'm the math guy, if that makes sense to anyone. You could explain it to me later. I'd like to know. So you're going to set up ahead of time. You're going to change the input to the function in a way that you can change it on the after you perform the encryption. So you're going to change your plain text, and then encrypt it, and then change your ciphertext so that on the other side you can do the same thing in reverse. So the operation and the input no longer correlate directly to the power be consumed because you're not encrypting your actual plain text, and your output is no longer the actual ciphertext of that encryption operation. Masking is instead of just performing the encryption, you do other stuff at the same time. So you do 2 runs of encryption on 2 different inputs so that there's another operation going on at the same time. And again, your goal is to make sure that the power consumption at any given moment in time isn't very strongly correlated as much as possible to the operation being performed at any given moment. And that's pretty much both of them, right?
Yeah.
Okay, awesome. So do any of you guys have any questions? I mean, did that make sense to anyone? I know the first couple of times that I read papers on this, it just didn't work for me at all. Do you have a question?
Using asymmetric cryptography or symmetric cryptography?
So asymmetric cryptography, if they've done it wrong, is usually going to wind up with a simple power analysis attack. But when it comes down to it, you're going to see the same. You wind up just using slightly different models depending on the algorithm being used. So no matter what, you're going to be able to use some sort of differential or correlation or template attacks depending on how much control you have over the device and what kind of inputs, what kind of outputs you're getting. They really apply equally to any encryption operation. It just varies a little bit on the model you wind up using. Does anybody else have a question?
What about using tamper protections?
What was that?
Tamper protections against a device, like try to tamper with it and erases the keys and you can't like get in there to do your voltage analysis and stuff like that.
So how? The problem there is you can't really, short of, so one thing that some manufacturers will do, and you'll see this on like your cable modem at home, if you were to open it up, the first thing you're going to notice is that you've got 2 extra jumpers that are sitting around if you didn't open it carefully enough. That's that sort of tamper protection, and that's going to, you've got a couple options of exactly where those can go, and if they're not in the right spot, then it's not going to work right. Well, those are easy to get around. You just figure out where they are, get another device, and take a Dremel to the case before you open it to make sure that jumper stays in place, and you've gotten around that tamper protection. Otherwise, I mean, you could try to do something like look at the exact resistance across all kinds of places, but there's enough variance in components and stuff like that where you're not going to be able to do that very well. I mean, if the battery gets low, that's going to go, oh, wait a minute, I'm being tampered with, I'm going to erase the key, and then your device no longer works because the battery got low. And I don't think it's going to be, I don't think the first thing you want in the manual for your game console is, if you ever let the battery go low, this is going to never work again. So that kind of thing really doesn't happen much, except to basically prevent people from opening the box in the first place.
Can you talk at all about any sort of specific products that you guys have done this on?
No.
Okay.
So mostly this is a research thing. This is a side project as we're going along. We haven't actually done this for like a client or anything. We wanted to, because we noticed that, like I mentioned, this is a cheap scope. Oscilloscopes have gotten really cheap compared to what they were even like 5-10 years ago. The bar for manufacturing something like this, if you remember how much I said just having somebody else do a one-shot of anything you want is like $100. That's from start to finish. You hand somebody a design, they create a PCB, and then pay somebody to sit there and populate it on top of actually ordering all the parts themselves. That's $100 for something like this. So that's as expensive as that gets. If you if you sit there and talk about actually designing something for mass production and you're going to order like 10,000 units, you're looking at a cost of like $5 a device. And I'm guessing for TI, even though they sell these things for like $10, they really are that cheap, their manufacturing cost is probably less than $2 a piece. So the thing there is, because it's gotten so cheap to make these things, you're starting to see more and more people. I mean, I actually managed to avoid saying it so far, but the Internet of Things is like full of these kind of devices. People that wouldn't normally, 10 years ago have even thought about creating something that beeps or has a blinking light and does something, are starting to do that now. And so what's going to happen, the idea for this research is what's going to happen when they go to Google and they go, okay, how do I do DES? How do I do AES? How good are those algorithms on the first couple of pages? Because, I mean, if it's not on the first page of Google, who looks past that, right? So how good are these algorithms on the first couple of pages of any search going to be against this sort of attack? On top of that, this one itself, how good are the devices themselves? Like this one is one of the newer launch pads based on obviously a newer chip that has an onboard AES accelerator. How good is that accelerator going to be? And well, given that it's TI that's creating this chip, I expect that to be pretty good because they probably paid cryptography research to, help them engineer that device to be protected against these attacks. But is that protection on this level of chip enabled by default? I know on this one it's optional. You can turn it on, you can turn it off. So how good is that? What is that documentation going to look like? What are these devices going to look like when somebody goes, okay, how do I do this? Let me ask a search engine, and this is what it tells me. And I know from my normal work in application penetration testing, the answer you get from the first couple of pages of any search engine on just about any security topic, unless you know what to search for, like how to do SQL, you're not going to get anything but injectable statements. I mean, have you guys done that recently? I'm assuming we have a room full of pen testers or something like that. You look at stuff for SQL and any kind of search for that, and you get concatenate these strings to get a dynamic query. I'm expecting about the same results to happen if you search for a cryptographic implementation in software. It's not going to consider hardware level protections. And that's some of the research we're still getting geared up to finally do, and do it across a wide range of chips and implementations, and ultimately get into FPGA implementations that are available on sites like opencores.org and stuff. And that was a very long explanation for a very simple answer. Does anybody else have a question?
How do you know where to start those traces? Is that because you own the chip and you actually?
So yeah, in this particular, she asked, where do you start the trace? Basically, in this particular case, it's a launch pad. So I told it to light an LED right before it starts the encryption, so I can cheat. And which is why, if you remember from the code, I'm pulling the data from the digital channels, so I can perform those cuts and get down to just the encryption operation itself. If you're not necessarily that lucky, you can sit there with the logic analyzer on there and maybe find a signal like that you can get, or maybe. If you remember from that video, and I can switch back to it and hopefully back up to a useful point. You can see where the operation happens. Right here, there's a huge drop in the voltage, like right when it starts. The scope, which I was able to set up last night, but this morning when I was recording the demo, I couldn't manage to duplicate. You can also set a trigger on that, so that at that point in the trace, it actually starts doing the recording, and then from there you'd use the sum of least squares on all the traces. Sit there, set up a template trace, and then use a whole bunch of math to just align them yourselves. And again, that was way too long-winded to. You get to answer the next one. Did that make sense?
Yeah, I guess I still don't understand how you would know, just like on any chip. Like, does this presuppose that you have to have access to the chip and understand what you're measuring and know which piece is doing the cryptographic?
So ideally, you're going to have, and if you look at the user's guide for that chip, which is not on that screen, over here. So if I were looking at a device with this particular chip on this family, the first thing I'm going to do is I'm going to pull up this document, and if you do a search in here, you'll pull up the fact that it's got a AES implementation on board, and then it's pretty likely in that case that it's going to be AES. Otherwise, you're going to do things like collect a whole bunch of traces, clean them up as much as possible using varying compression techniques. And based on kind of what you can look at and see, if you remember from Alex's slides earlier, you can see in these, and I just overshot horribly. You can sort of see that there are like 16 like grouped squiggles and sort of making educated guesses from there. And start to narrow that down. If you see like 1024, you're going to go, hey, wait, that's a large key. That's probably some public key integer factorization-based math problem algorithm. So like RSA, DSA, something like that. Otherwise, you're going to look at how many groupings there are like that, and maybe go, okay, this is calculating an HMAC or whatever. So. And then go from there to try and build your model. Otherwise, failing any of that stuff, you're going to sit there and try a whole bunch of models, and hopefully one of them, works. And if not, then you get to write a nice report that I really hate writing, because it's all about what you did and not what you found. And I really hate writing that report. Fortunately, well, actually, kind of unfortunately, that's not a report you wind up writing much. At least when you're doing applications, because, well, OAuth top 10 hasn't changed much, and that pretty much tells you what's going on there. Wait a minute, you were supposed to answer that one. You're cheating. Anybody else?
What particular model scope is that?
This is a Rigel. Wait.
That's a Rigel.
Right there.
DS1102D.
Yeah, it's this is a 100 megahertz scope with a logic analyzer in it. It is the level up from their absolute cheapest one, and it's $700. Oscilloscopes in general go from $300, which is their 50 megahertz, no logic analyzer on it, and you're supposed to be answering these. Oh, right, you didn't do the actual research to figure out what scope to get. So from there, they go up to at least 20 grand. And at that point, you're talking about a scope with at least 4 analog channels and a bandwidth of at least 1 gigahertz. And for the most part, if that's the kind of scope you're targeting for this kind of work, you're probably working for cryptography research, because that's about all they do. Like I said, they own the patents and the preventions. They did the original research on this stuff. They're really good at it. He's actually taking the class from them.
Well, they say that 200 megahertz scopes are all they ever really need.
Yeah. So for most of the devices you're going to wind up using, this is like the clock on this thing maxes out at 20 megahertz. So as long as you have a decent 50 megahertz scope, that should be all you need. You really need, as far as I can tell, about twice the clock speed and bandwidth. So if you're talking about embedded devices and stuff like that, unless you're attacking a phone, you're looking at worst case 100 megahertz for just about any ARM chip you're ever going to look at. So like you said, 200 megahertz on that scope, and you're good. Anybody else? Is there anybody hiding behind the light that's holding up their hand? Because I can't see over there. No? Okay. Well, thank you. Look at that. Look at that.
Alright, well that's it for the seminars. We have our reception up at the pool later on tonight at 7 o'clock, so go get some dinner. And we've got a bunch of snacks and drinks and stuff like that up at the pool starting at 7. So see you guys there.
Thank you. Nice to see you again.
Yeah, same here.
Yeah, I was here last year.
Yeah, yeah.
My first time, so.
Everybody, we did
Oh, great.
film all day today, and so these DVDs will be out starting tomorrow afternoon. On the table we'll have somewhere, so swing by and see us.
Oh, that's so good.
Yeah.